Right, welcome back to our next section. Which we have is the new section of continuity and the one-side limit. Right, it's the section 2.4. One-sided limit and about the continuities. So an arbitrary function at the point C. Right? And the first thing is we had seen before, right? Limit approach from the left, from the right of the x value on the path of function. They match together, we call that limit exists. Right? And each path, when it's approaching, is called one-sided limit. Right. Limit of x approaches C from the left side is we have a superscript, a negative sign, because this one is just a little bit lower than C, which means it's the limit approach from the left. That is stand for limit of f of x when x approaches to C from the left side. Right, so along the path of the function, it approaches to the C, right, along the path of f of x from the left. That is this notation, and we use C minus. And also the other side is when the x approaches to C plus. That is approach along the path to the value C from the right. Similarly, that's limit of f of x when x approaches to C from the right. Right, so this one is path through the x equals C, or to the x equals C, approach from the right side. That is the limit from the right side. The C could be any number, positive, negative, zeros. And also from the left side is when it's from the left. So that was called one-sided limit. And of course the limit exists when the left side equal right side of the limit equal a certain value k, and that k is the value of this limit. For the value k here, if the limit exists, if the limit approaches to C from the left side of f of x equals the limit of f of x as x approaches C to the right side, and that equals a certain constant. And in that case, the limit of x approaches to C of f of x is equal to this k. Well, is equal to this k. So that is one-sided limit, and that's the relationship when the limit exists and related to the one-sided limit. As we see before, graphically, right, if the limit approach from the left and from right meet at the same point, we call that the limit exists, and that is our limit. That is the thing. And for the continuity, for the continuity of function, what we can call this function is continuous at C, right? It's clearly is a function that goes on with its path, right? So how we explain it goes on with path is, first of all, the function has to be defined. Right, the function has to be defined at C, and also the second thing we need to check is the limit of f of x when x approaches to C exist. Right, so which means we're looking for the left side, we're looking for the right side, they meet at the same point. Right, both one side limit exists and meet at the same point, that called the limit exists. And the last thing is where the function defined and the limit of the function at C is supposed to be the same value. Well, we cannot have infinity as the limit, we cannot have limit not exist. Right? And also the limit to be a constant needs to be match our defined function value. Right? So that is called it's continuous at C. Right, let's get a open interval. So define definition. A function is continuous on an open interval from A to B when the function is continuous at each point. For every point inside our A to B, even though a little bit greater than A or a little bit smaller than B when it approaches, so everything should be following this, all of the conditions. So I have three conditions, all of them satisfy with a function is continuous at a certain point. So every point inside, we have that condition. So we will get maybe not that smooth, but we must get a continuous curve that at least it's connected to that together. So regardless the end point how it looks like, that is how we get a function has an open interval in between A and B. Right, so that is continuous on an open interval. every point in that open interval should be continuous. And when we're saying continuous at a special point, that is function need to be defined, limit should exist, and limit should equal the function value. Our function should be defined, limit maybe along the path will exist, right? But we don't care what is inside, but now the function should be defined at the point that will make the entire graph connected together. Right? That's what we call continuous on a certain point. And continuous on an open interval, again, is just every point inside is continuous. So consider that the all real number is an open interval, right? That doesn't have the end points, which is simply from negative infinity to positive infinity, is an also open interval. A function is continuous on the entire real number line, is everywhere continuous, such that we have seen was the polynomial, right? N degree polynomial, n degree polynomial, or what we have seen was the exponential functions also is continuous everywhere, right? It's everywhere continuous. It's continuous on the entire real number line. So that's another more definition, which basically is based on the domain still, right? If we have function defined and it's not piecewise function, it's a simple function, then most time it will be continuous on its domain. Right? For piecewise function, we'll check the other conditions to see how each piece looks like and where is the end point, or where is the break point. But that was the definition here. And of course, when we discussed about continuity, we will have something called breakpoint, which is officially called discontinuity. Discontinuity. So there are two types. The first type is called removable discontinuity. On an open interval a to b, there is simply a hole there, which the function is not defined at the value c. Or it could be defined at the value c. Or it doesn't matter if it's defined or not defined. That type, if we give a definition on the point where it is break, we can make it continuous, which is, in other words, it is removable. That we call it is a removable discontinuity. Removable discontinuity. Right, so removable discontinuity, we have the case that the limit exists, fx may or may not define at x equal c, but even though it's defined, the limit will not equal f of c. Right, so that is called removable discontinuity. It is a discontinuity at c. The special type is called removable. The limit exists, which means you can find one side the limit from the left and from the right. And you may see the function is defined at this point, or maybe not defined at this point. But even it could be defined, the limit of f of x when x approaches to c is not equal the function value. If it's undefined, certainly it's not equal. If it's defined and defined somewhere else, we can see it's not equal, right? Therefore, we get a breakpoint here. That type is called removable discontinuity. And another type of discontinuity is called non-removable discontinuity. Non-removable discontinuity has especially that limit x approaches to c f of x not exist. All we have seen is does not exist. Right? It could be like something we have seen before, the limit does not exist. Could be that the one-sided limit is not equal. Or could be a case. Or it could be the case that at c, the one-sided limit has one value when x approaches to the left, has another value when x approaches to the right. That is, both sides of the limit exist, but they don't match. Like especially we have seen some piecewise function before has that type, which this is jump. Which simply the two breaking point here. The breaking point here is a jump, right? From one value jump to another value. That is especially called jump. But in total still that basically is still the non-removable discontinuity. Another type is simply the limit not exist because it is infinite. When it occurs at a infinite, when it occurs does not exist of limit, since the limits of either side or both have a vertical asymptote, that is not exist because it is infinite. That is the type of infinite discontinuity. But either case, right, when we find a limit doesn't match, or when we find the limit to be infinity for either side of the value, that is called non-removable discontinuity. We have no way to redefine a function value to make the function to be continuous again, right? We have no way to do that, which these are called non-removable discontinuity. So to wrap up, when we check the continuous, function value need to be defined, limits need to be exist, and these two should equal. Right, so we need to check the limit, we need to check the function value, we need to make them make sure they are equal, then we can say a function is continuous at C. Right, for removable discontinuity, the limit exists, but maybe not equal, right, to the function value if it's defined. If function value is not defined, then of course nothing will happen, right? That will not equal f of c. If f of c defined, if f of c not defined, that technically of course not equal, right? That is removable discontinuity. We check the limit and we check the function value, right, to see if they are matched or not. And non-removable, non-removable discontinuity if the limit does not exist. How we check does not exist, at one side the limit that doesn't match, right? Or the one side limit we get in infinity, that we can say the limit does not exist. Right, so all these strategies, right? All these strategies to check for continuous, removable discontinuity, non-removable discontinuity, all of them we need to do is check the limit. Right? If strategy, right? All the steps, right? First check the one side of the limit. If they match. Right, if they match, we say, well, the limit exists, right? At least cannot be non-removable discontinuity. And so if not exist, then we say f of x has a non-removable discontinuity if limit does not exist, we could stop at this first step to say conclusion is f of x has non-removable discontinuity at x equals c. Right, then the second step, right, we check f of x. F of c, right? If f of c undefined, or the limit we found is not equal, then we have a removable discontinuity. Right, so if we get first, it is not exist, we get the conclusion already that is non-removable discontinuity, we stop there. Right? If the limit exists, then we try to find f of c. Right? If fc is undefined or limit at x approaching to c of f of x is not equal to function value, then we have conclusion say it is removable discontinuity. Right? If the function value equals its limit, f of x is continuous. Right, so 3 steps to show everything. Right? If satisfied here, we stop. If it is removable discontinuity, also stop here, and the rest case is remaining to be continuous. Right? So continuous, we check everything. For non-removable discontinuity, we have just one thing to check: the limit not exist. For removable discontinuity, we have 2 things to check: limit exists, but doesn't equal function value. Right? The third thing is, well, if the limit exists and equal the function value, then it's continuous. Right? So there are many things to check. So let's see. The question, right, to discuss we see, well, here is a rational function, f of x equal 1 over x. Well, we know that the domain is all real number except the denominator equals 0 for rational functions. So in this case, f of x continuous everywhere besides possibly at x equals 0. We need to discuss which type, or if it may be continuous, or which type of discontinuity it is. Right, but the rational function is everywhere defined, but besides the denominator equals 0. Right, so it should be continuous everywhere besides the possible x equals 0. Right, so we check the limit first. For the one-sided limit, we have nothing else to do but just substitute the value. For 0 from the left, well, we could, if you understand that 1 over a very, very tiny number gives us infinity, that is okay. But you could still use the very, very small approaches to it, which will get 1 over negative 0.0001, or about this value. But from the observation that we get negative 1000, even you get more zero, that number will be bigger, right? So therefore, this limit is equals to negative infinity. I will talk about the infinite limit in next part, but that is what we have here. Right? We could just substitute using a value very close to it and see what we have for the one-side limit. Then once we get one side to be infinity, we could make conclusion that the actual limit of x approaches 0 of f of x does not exist. Therefore, f of x equal 1 over x has a non-removable discontinuity at x equals 0. And continuous elsewhere. Well, you don't have to write the continuous elsewhere when you list out saying the discontinuity is at x equals 0 and non-removable is in this case. I pretty much can understand, you know, you're assuming that everywhere else is continuous. Right, so that will be good enough. By saying, well, it's a non-removable discontinuity at x equals 0. Right? The limit does not exist. That shows it's a non-removable discontinuity. Right, for this rational function is a little different. Like the previous questions, right, from the last couple sections before, we have seen this type of rational function can be simplified. Right, but still, right, for rational function, only possible discontinuity will be its denominator equals 0. Right, so which we solve it to get x equal 1. Right, simply because the denominator equals 0, the function is not defined. Right, so we check the limit. Limit one side from the left, that is x minus 1, x plus 1. Oh, which is we get a linear equation, right? Linear expression. We can simplify or reduce the x minus 1, we get x plus 1 only. Then the one side limit has to be 2. And similarly, Right, the limit from the right side is also 2. Well, you could, if you can figure out this in the beginning, you don't have to do the one-side limit. You could just say, well, the limit of x approaches 1 of this whole expression, since it can be cancelled out, I can find the limit by itself to be 2. Now clearly, the limit equals 2. However, f of x is undefined at x equals 1. Right? See, even though the limit exists, but fx is undefined at x equals 1, that is the case that the function and the limit cannot match together. Therefore, f of x has a discontinuity, which here is removable discontinuity. At x equals 1. Inside its domain, everywhere else is continuous, but only we have a removable discontinuity at here x equals 1. Right, so that type is rational function we'll discuss about, and maybe we can see something else. For one side limit f of x to be x plus 1 when x is less than or equal to 0, f of x is defined as e to the x for x to be bigger than 0. Right, so we'll discuss by starting to say, right, to observe the function itself. The function we have, each piece is, the first piece is a polynomial, even though especially it's a linear function. When x is less than or equal to 0. The x bigger than 0 is defined as e to the x. Both of the piece under each of their domain is continuous. So f of x is continuous in each piece. Or even though it's a piecewise function, it's continuous in each piece. Since we have line and exponential function, right? Both of them are domain. They are continuous inside its domain. Right? Not only inside its domain, but especially, of course, inside its defined interval. Right, therefore, the only discontinuity possible discontinuity is at its breaking point, which is x equals 0. Right, that makes sense. Each piece should be continuous, then the only discontinuity will occur at the breaking point. So we do not know if we can find a continuous or we can find a discontinuity on here, right? So that is only possible discontinuity. So when we do that, the strategy we have put it already, right, to check if the limit exists. Right, if limit exists, then we move on. If not exist, then we have a non-removable discontinuity. If a limit exists, then we check if that equals function value, if it equals, or if the function defined and equal, if function is defined and equal, then we have continuous. If function is undefined, or even it's defined but not equal, then we have a removable discontinuity. Alright, so let's check the one-side limit still. Since for the piecewise function, when approaches from the left, approaches from the right of the breaking point may yield a different value caused by it using a different function, so we need to check separately. Right, the limit from the left which is a little bit smaller than 0, we use the function piece is x plus 1, which in this case, just substitute in 0 plus 1 is 1. And for the right side limit, it approaches from the right side of the function, which is approaches along the path of e to the x. That is e to the 0, which is a little bigger, but doesn't matter. E to the x is continuous at 0, so approaches from the right is still e to the 0, that is 1. Therefore, we get the limit x approaches to 0 of f of x, since these two value matches, right? That equals 1 of the limit. And we find f of 0 is defined on the first piece. Is also 1. We have the limit equals the function value. Therefore, f of x is continuous at x equals 0. So actually it possibly is discontinuity, but actually in our case here is continuous. Okay, so hence f of x is everywhere continuous. Right, so that happened that piecewise function, we have to find one-side limit afterwards. We get the limit exists. We evaluate the function, we have function equal to the limit. Then the possible discontinuity actually in our case after we figure out is continuous. Right, hence the function is also continuous because we had discussed before that f of x is continuous in each piece. Its only breaking point or possible discontinuity is at x equals 0. Right, therefore we get a conclusion at the end. Not only it is continuous at x equals 0, but also it is, our function of x is continuous everywhere.